Thank you very much. First, I wish to thank the organizers for the very pleasure to be here today. And then I want to talk about the speed of random walks on solvable groups. So let me first present the setting. So I want to consider a group gamma. And this group should be finitely generated. So I have a finite generating set S. And I usually think, so I might not write it down later on, but I usually think that S contains its own inverse, and the neutral element I consider a generator. And of course, when we have such a group, we have the word distance associated to it. And well, we can view this as the distance in the Cayley graph associated to it. And now I want to get interested in random walks on these groups, and mainly in simple random walks. So what is a simple random walk when we have a group with a generating set? It's just looking at products. Zn is a product of n elements, S1, S2, etc., Sn, where all the Si are in the generating set. They're independent. And the probability that Si is equal to a given generator is 1 over the size of the generating set. Right? So one way to picture this is to say we have this Cayley graph of gamma with respect to S, and we have a particle at a starting point, and then as time goes on, 1, 2, etc., up to n, the particle randomly moves to its neighbors. So this is the simple random walk, and it's interesting to consider this. And today I want to consider mainly speed of random walk. So the speed of a random walk, this is also called the drift of the random walk. This is a simple quantity that I will denote it L, depending on gamma and S. And this is just the expectation of the distance between the position of the particle at time n and its starting point. Right? So this is a very simple definition. So S, the generating set, is involved in two manners in this definition. One that we understand very much. It's involved in the choice of a word distance. But then we know that if we change the distance to another distance with another generating set, this just multiplies the lengths up to multiplicative constants. So this does not change a lot. But also, if we change the generating set, then we change the sequence of products we obtain here. And how does this depend on the generating set? This is still an open question. So I don't want to hide this open question. My tendency will be to make as if this would not depend this, but it's an open question. So I want to mention it. Open question. What if we change the generating set? So this is not clear. However, even if we cannot answer this question, there are still interesting results about speed. So let me remind of somewhat old results. So probably the oldest result about speed is due to Harry Keston in 59. And this says that if the speed is sublinear, then the return probability does not decay exponentially fast. So the return probability, that's the probability that the random walk is back at its starting point at time n. This is not an exponential function. It's not equivalent to an exponential function. And this criteria of return probability, this is equivalent to saying that the group gamma is amenable. Right? So this is a first theorem. So this gives a criteria to tell the group is amenable, and also vice versa. If we know we have a non-amenable group, then whatever generating set we choose, the speed will be linear, right? Of course, the speed cannot be more than linear because the length of this product certainly cannot exceed n. And this is not an equivalence, and an equivalent characterization has been given by Kajmanovic and Verschik. So this is also a very famous result back to 83. Having sublinear speed is equivalent to having sublinear entropy. And this is equivalent to having a trivial Poisson boundary. So this is equivalent to say that the Poisson boundary is just a point. So this theorem is interesting because this makes speed an interesting quantity when the Poisson boundary is a point, right? In usual, when you want to study a random walk, the first thing to do is to find out what is the Poisson boundary. And the Poisson boundary somewhat rules the behavior of the random walk in the long term. And when this Poisson boundary is a point, you lose all the information, right? This just all trajectories look more or less the same. And if you want to have information, you should look at something else. And from this theorem point of view, then naturally you can look at entropy or our speed. They will tell us some things about how the random walk behaves. And this theorem makes this very natural question: what are the possible behaviors for speed of groups? What are possible speed behaviors?
Isn't it solvable?
Is this equivalence is
in one direction is due to Arrhenius.
Okay, so I missed something here. Thank you. So now, from now on, I want to list essentially some examples of possible speed and some results that. So what are the examples known about speed? So the 0-degree example, if you take a finite group, then of course the speed is less than the diameter, so it's some constant. It's equivalent to a constant. So then the second class of group that you can look at, very natural, is a abelian group. And here it's mainly the central limit theorem that tells you what happens. Okay, the central limit theorem tells you a lot of things. It tells you how the random walk distributes in the long term. But in particular, concerning speed, this tells that the speed is equivalent to square root of n. Right? This is the good scale. And this behavior we call diffusive. And in fact, so this is true for any abelian group. And once you know something for a abelian group in group theory, you usually try to see if this also works for more general class. Still example, nilpotent group. And this is the case for nilpotent group. And this is the same thing. This is due to, I think, Hebbish and Saloff-Kost. And these are not the only groups. This is also true for many polycyclic groups. And I think, yes, this is due to David Revel and Ruth Thompson. They're student of Lawrence Salof-Coste. And this is also true for a group that I will come back to later on, which is the Lamplighter group. So all these examples have speed square root of n. So in group theory, for instance, if you think about growth, you tend to think that abelian and nilpotent groups are the smallest groups. So somewhat we expect that the speed would be minimal for them, right? Besides finite group, of course. And this is known to be true. This is a theorem due to Lee and Peres. So if gamma is infinite, then the speed is bigger than constants time root n. So this question, what are the possible speed behavior, now comes down to what are the possible speed behavior between square root of n and n. And so what happens in between? So we know some things in between. So the first series of example is due to Anna Erschler, and this is based also on Lamplighter groups. So second type of example, so I have this gamma 1 here, and if I put gamma I to be gamma I minus 1 rest product z, then the speed function is going to be equivalent to n to the 1 minus 1 over 2 to the I. In particular, if you have gamma I a diffusive group, then this will be n to the 3/4, and then you get 7 over 8, and so on, sequence of exponents. And there's also a variation on this. If you change the z into a z square, then you find n over iterates of the log. And I guess you can mix these two to get some kind of powers of the log and so on. And so this is due to Anna. And there are more behaviors. For instance, Anna showed that the speed of a random walk can be arbitrarily close to linear. There is no gap between linear and sublinear. And this thing also can oscillate. In fact, it can oscillate with a maximal magnitude between square root of n and n. And so there are some examples. And then there is a theorem, which is due to Amir and Amir-Virag. So they are able to obtain a much larger class of function. So if you have a function that is between n to the 3/4 and n to the gamma for some gamma strictly less than 1, mainly any function like this, then there exists a group and a generating set where the speed function is comparable to this given function. So this somewhat tells you that anything can happen above 3/4. Okay, there is a small condition here that this gamma should be less than 1, but it can get arbitrarily close to. So this is a very rich possibility of behaviors. And also they have a conjecture. Okay, I'm not sure the exact statement of the conjecture, but I would say the conjecture says that this would be true if you replace 3/4 by 1/2, right? Okay, with 1/2 instead of 3/4.
What is the condition of f of that? It's non-decreasing.
So there is some mild condition. yeah, it should have some regularity in some sense, but somewhat, of course, this function cannot be, I mean, it has to be, for instance, subadditive. And this is, the kind of restriction is like this. So,
What kind of groups they got? Solvable branch groups?
so these are branch groups. So these ones are not solvable groups. Right, all the previous examples I mentioned, they are solvable groups, but these ones, they're not. And so now this somewhat leaves us the open window is between square root of n and n to the 3/4. And here is the theorem I want to present today. So the theorem is that whenever you pick a lambda between 1/2 and 1, and this is really, I mean, really in particular, this is true, and this is the heart of the theorem between 1/2 and 3/4, then there exists a group with generating set such that gamma is solvable. And if I look at this speed function, then, okay, what I would like is that this is n to the lambda. So I look at the log of this over log n to track down the lambda, and I would like this limit to be lambda. And this I cannot do for now, but what I can tell is that the lim sup is lambda. So I can prescribe any lim sup between 1/2 and 3/4. So what is interesting in this, of course, is that we go in this region where we didn't know much. And also the new thing is that now this is uncountably many behaviors among solvable groups. So this was not the case in these examples. And so this is the nice part of the theorem, and now I should tell the truth. What is the bad part of the theorem is that I can also compute the lim inf. And the lim inf of the same thing is just 1/2. So nothing interesting here. So this is part of the theorem, but not the interesting part. So let me draw the picture. What happens here? What happens here? So we have time n, and then we have this exponent 1/2. We have the exponent 3/4, and we give ourselves some lambda in between. And now the function that I can obtain looks like this. It's 1/2 for a long time. Then it goes to lambda, and then it's 1/2 for a long time. Then it goes to lambda, and so on. And the problem is that these things here are long, and these things here are short. That's the thing that is not so nice. Of course, if I could make these bumps arbitrarily long, then I would get exactly the limit by taking a product of two groups and having the small ones during the higher ones of the other. So okay, so this is the statement of the result, and now I want to spend some time essentially giving the proof of this theorem. And first, I want to remind really basic thing about Lamplighter groups, because the construction of the group will really be based on what happens for Lamplighter groups. So let me start with the simple one, the usual Lamplighter group. This is just the group of functions from z to z mod 2z, semi-direct product z. And I should tell you the generators. The choice of generators will be important. So there are the generators where the lamp is all 0, and then plus or minus 1 in Z. And there are the generator where I do plus 1 in the lamp at 0 and nothing at the other lamp, and 0 in the group. So the usual picture in Lamplighter group is the following. You have a function like this with finite support. I should say this. So we can view this as a street, and we have lamps in the street. And then this position here, we view this as a lamplighter, some guy who will turn on and off the lamp. So giving you an element in here is giving you a configuration of lamp and the position of the lamplighter, right? There is 0 somewhere, and the lamplighter guy, he has his house somewhere in 0. And now our lamplighter is going to perform a random walk. So it's very natural for a lamplighter to perform a random walk because, I mean, when you think of it, being a lamplighter is not a great job. So there's a slight tendency to be alcoholic if you have a lamplighter. So you drink all day, and then night is falling and you have to turn on the lamps. So our lamplighter, he exits his house, and he's completely drunk, and he's turning on and off lamps anywhere, and at some moment in the night, he's too tired and he falls asleep somewhere. And then in the morning, he wakes up. Now he is sober, possibly with headache, but he's sober. And then he wants to go back home as fast as possible, for instance, to take a shower. But he has to turn off the lamps. So now on the way back, he's going to turn off the lamps in the most efficient possible way. So he's going to take a geodesic path in the group to solve this. And this is how you think about estimating the speed of the random walk. So when he wakes up, he's somewhere. And the important question for him is, what are the lamps that are possibly turned on? So what happened during the night, he random walked on this line. And so he visited a certain number of sites. And how many? This is just the number of sites visited by random walk on Z. So the number of lamps visited, this is comparable to square root of n, right? This is essentially, as I said, the central limit theorem. So how long does it take him to go back home? Well, it's easy. He just goes to the rightmost lamp, turns it off, goes to the leftmost lamp, and turns off appropriately all the lamps, and then goes back home. So the speed is essentially square root of n up to multiplicative constant. So the speed in this group is comparable to square root of n. And you see that the choice of Z mod 2Z is not very important. I can take any finite group instead. And till example, I'm going to choose later on this one. The reason will be very clear in a minute. And what happens now if you replace this Z mod 2Z lamp by Z? Then, of course, the lamps visited does not change. But there's a question, what is the height of the intensity in a given lamp? So this is related to the time spent at a typical lamp. And this time spent, well, let us do the most obvious thing. You have time n, and you visit root n sites. So typically, you expect to spend n over root n time at each lamp, which is just root n. And this very naive explanation can be made precise, and this actually essentially works. And now, what is the expectation of the distance in a typical lamp? Well, in a lamp, you have group Z, and you made root n steps of a random walk. So this is root of root n, which is n to the 1/4. And now what is the expected distance in this group? So you have root n sites, and at each site you need to spend n to the 1/4 time. So this is just the product, root n times n to the 1/4, and that's where this 3/4 comes from. Right? So this is, and of course you need to move in the street, but this is like root n distance, this is negligible. And you realize again that this group Z here is not so important. Any diffusive group would do the same. And I can choose a diffusive group that only very slightly differs from Z, is the infinite dihedral group. Right? This is very simple. So okay, this was to remind you of this story. I think this is not difficult. And now I want to prove a proposition that will be the main step toward the theorem. So here is the proposition. There exists a universal constant. Till example 1000 does the job, such that whenever you give a lambda between 1/2 and 3/4, and whatever positive k you choose, there exists a group gamma and s, such that the speed function for this group satisfies a number of things. Well, I want to say that when n is less than k, this behaves like square root of n. So this will be equivalent to square root of n. And I want to say the constants are independent. So to be precise, I will say that this is exactly the speed on this group with Z. Right? So this is L Z mod 2Z times Z mod 2Z res Z of n for n less than k. Then I want that in the long term, this is no more than square root of n. So this is less than C prime of n for n large, where C prime square root of n for n large. I want this to never exceed n to the lambda. And I want this to exceed n to the lambda over my universal constant for some n bigger than k. So let me draw a picture. These are 4 conditions, but if you draw a picture, this is very clear what speed function I want.
The first, it should be equal.
Yes. Thank you. Equal to this one, which I think of root n. So the picture is, okay, it's, there is 3/4, 1/2 lambda. And now I have a parameter k here. And the speed function should look like square root of n until time k. Then after time k, it should bump and hit lambda. And then at long time, this should be like root n. Right? This is exactly the speed function that I want. And now let me explain how to construct such a group. So this is proof of the proposition. So I have a group. So it will depend on k, and it will depend on another parameter L. And the group I take is extremely simple. It's the rest product between a dihedral group of size L and Z. So the dihedral group, this is very well known. This is the group generated by 2 elements. One is an involution, the other also, and their product to the power L gives the identity. So let me just say a word about the generating set, the Cayley graph of this group. This is extremely simple Cayley graph. You have generator A, generator B, generator A, generator B, and so on. Right? That's as simple as that. And I have to tell you a generating set. So far K didn't come into play. So now K has to come into play. The generating set. So of course, I take the walk generators, usual walk generators. And then I need to take generators of the lamps. And I have two types of generator, A and B. And I take A at position 0. And I take B at position K. Right? Now, okay, maybe let me tell you what the picture is. And this has slightly changed from our lamplighter. Not much, but. So the picture is the following. I still have the street, but now the lamps, they are dihedral groups. And it's not true that I have a lighter walking. Now he improved, there was social progress, so he has a bus now. And this is a bus. The length of the bus is K. There's a driver. Right, so he drives. And there is one A lighter. And there is one B lighter. Right? And now, okay, our lighter is not alone anymore. So as he has new friends, it's a good reason to party, and so he should get drunk and perform another random walk. So at each step, the driver either goes right or left. This is really random, he changes gears. And the lighters, they just by the window switch on and off their respective lamps. And of course, in the morning, then they'll have to find out the shortest way to go back home. And so what happens? If n is less than k, then here, only the B lighter will never make it to the starting point of the A lighter. So the A lighter will light on some A lamps, and the B lighter will light up some B, but they will never interfere. So the Cayley graph coincides with the Cayley graph in the following group. Which, if you think about it, this is just the dihedral group of size 2. And for n much bigger than k and L, of course, I have the impression that L is just finite and k is like very cheap. So what I see is finite with z. So the speed will be equivalent to root n. And what happens in between? In between, I have to choose the good L, the good size of lamps. Why? If I look at the rest product with the infinite dihedral ramp, then this will be like n to the 3/4. Of course, only in the long term, but this will be like this. So if I take L equal 2, I have square root of n. If I take L equal infinity, I have n to the 3/4. So as I increase L, I should eat n to the lambda somewhere in between. The only condition is that, okay, I want to apply intermediate value theorem, and this works only for continuous function. So there should be a lemma of continuity. And the lemma is very simple. There exists a constant c, universal, such that whatever k and L I choose, when I look at the speed in the group where the lamps are in the dihedral group of size 2L, this is of course bigger than for L. And this is less than this universal constant times this group, right? So this is a lemma. It's not very.
Write gamma KL and gamma K2L.
Yes. Yeah.
Generating sets.
I should remind you that K is fixed and the generating set is like this instead. Indeed, thank you. And now in order to get the proposition, I just need to choose L minimal such that this D2L Z at K exceeds n to the lambda for some n bigger than K. Right? And this gives the proposition. And now once we have the proposition, of course, in the long-term behavior, this is nothing else than square root of n. So this is not interesting. But now I want to stick many copies of such groups in order to multiply the bumps. And this is, again, fairly easy. So proof of theorem. Now I look at the diagonal product over some sequence I of this gamma of Ki Li with generating set S Ki Li. And in the iscopy generator, then I always have the same walk generators. I always have the same switch for A lamps, but the switch for B lamps, they move along. So the picture is the following. Now you've got many lines, and you've got buses on these lines. And now, as you made such a progress, you have a huge company, you have lots of drivers, so you're just in the office and you're telling the drivers move left or move right. And now you shouldn't drink with your employees since you have so many of them. So you're drunk in your office and you're giving them orders, and they move along, somewhat gently, somewhat not gently. So this is somewhat messy what happens here. And so from the theory of the groups, this is like too much, so I should simplify this somewhat. I cannot control all at the same time. So I put this, and now I cut them to make them finite groups. So now the circuits also vary, right? And as long as I choose Ki plus 1 sufficiently much bigger than mi and all the other constants at step I, then the previous factors are negligible. So then this bump, I can reproduce, okay, way long afterwards, but I can have an infinity of bumps. And so this proves the theorem. And okay, I said the groups are solvable, and this is obvious from the construction because each of these groups is just 3 solvable. So these are 3 solvable groups. And the story ends here. Thank you.
Thank you very much for this nice lecture. Any questions, comments?
You go up to 3/4.
Yes, so this construction goes to 3/4, and then it's somewhat, it's not completely true, but in the spirit it's true, that if you have some group, here you have some exponent, here the speed is like n to the gamma, the speed you obtain is like this. So if you have something between 1/2 and 3/4, it will move between 3/4 and 7/8. And then the groups will not be 3 solvable, they will be 4 solvable. And so on, as long as you get closer to 1, you increase this.
more questions?